Select star from table is a universal SQL syntax that will basically return all columns in the table that you're selecting. It's been said that select star is slow, and to avoid it, it's like don't return on column because it is slow. But I want to actually dive deep into the reasons of why select star is slow. Some of these reasons you might already know. Hey, returning 50 columns is of course slower than returning one. But I think some of these reasons you might not have think about, because it really involves understanding the entire stack and the backend engineering fundamentals, and specifically the network aspects of things as well. And of course, programming logic, memory management, how the OS works. All of this really affects the performance of your queries. And selecting all the fields, while convenient because you don't have to enumerate the fields you want, it can impact the performance in general. So I wrote up an article on Medium that I'm going to review in this video, and I'm going to add my comments and going through the reasons of all of these things. How about we jump into it? All right, so let's get started. How slow is select star? Let's read this little bit of a paragraph and then start discussing this stuff. In a row store database engine, rows are stored in units called pages. And boy, don't get me started. We're already in the first sentence, and I already thinking about this stuff, right? After I write this, and then coming back and says, wow, there is just so much to these things. Like a page and a block is the most overloaded term in software engineering, that is, right? You have no idea how the word page shows up in the entire stack, from the database to the file system to the operating system to the SSD itself, right? Or to the drive itself. The pages are all different in sizes, and specifically here we're talking about database pages, right? And database pages are really fixed size. Like all databases that I know of use fixed size pages, or just think of a structure, I suppose, with headers, and the content of the page is essentially mostly rows, or if you have like a column store, it's going to be the columns, right, for that first row, and then the columns for the second rows. It depends on the implementations. And if you have documents, it's going to be the documents. If you're going to have graphs, it's going to be the graphs, and so on, right? And of course, this a little bit changes if this is an index page versus a heap page, but essentially that's the gist of it, right? So everything is a page effectively. Right? And this is an example I put where this is how the Postgres page looks like. There's a bunch of headers, and these are called the tuple pointers, and they specifically specify where does this tuple start in byte 134, and it has a length of 20 bytes, right? And the second tuple starts in 155 and it has 10, and this is basically lives in page 0, right? So that's how pages are. But so technically speaking, if you really think about it, the row is stored in the page with all its columns. So the first question is, when I read a page, I get all the rows and in that page, and I get all the columns. So technically select star should be cheap, right? Because I already have all the columns in line, quote unquote, in line in that page, right? Because that's how row stores things. Basically, we're dealing with transactional workload in this case. So we'll always assume row store. But then why people tell us that select star is slow? And that's basically what we need to understand here, right? You see, every time you fetch, let's explain first of all, how do we read something, right? I want to read a row, right? Select star from table where ID equal 1. Let's say this is a student ID, right? So assuming there is no index, what the database will do is, okay, we're going to do a full table scan. So there is your table, and the table is literally one file, and it is organized as an array of these pages that we talked about, this fixed size pages. So what the database will do is, I need to do a full table scan. And what that means is I need to scan the pages one by one in the file. So I'm going to read page 0 from the file. How do I get page 0? Remember, when you read from disk, you have very certain operations when you want to read, right? You read, you specify the file descriptor, where do you want to read from, where the starting position is, and how much bytes you want to read. That's it. And the how much thing is, I think, up to 2 gig. That's the limit in Linux, at least, right? That's all you got. So how does that convert to pages when it comes to databases? Well, once you understand the fundamentals, this is all simple stuff, right? The database, to read page 0 starts at the 0th position in the file. So the offset is 0, and the page size is also fixed, right? In Postgres it's 8K, in AnuDB MySQL is 16, right? And so the length is 8K, it's all fixed. You might say, Hussein, how do I read page 7 then? Well, 7 is literally, page 7 is 7 times the length of all the pages that went before it, right? So 7 times 8 plus 1, so you actually start the next page, right? The next byte, and then you read 8K, right? And so on. That's basically how you read pages. Once the database reads these raw bytes, and these in reading this there's a little more to it than just, I say read, right? I don't like to say these things anymore. I like to understand how things work. There's layers and layers and layers of things underneath that read operation, right? There's the file systems involved. The bytes are converted into file system blocks, and these blocks are mapped to the SSD blocks or the sectors or in the drive, and those blocks are physically retrieved, because the API to read offset length is not consistent across the storage driver, right? We don't read bytes, we read blocks, assuming this is a block storage, right? We deal mostly with block storage, so everything is a block. So if we want to read a single byte, you read whatever the minimum number of block the file system allows you to, and that's 4K in most cases, right? So I'm gonna talk about this maybe in another video, so just so I don't go off track here. But once you read that, once that page is read from the SSD, transferred to the file system into many blocks, and now we have the raw bytes. The operating system have the raw bytes in memory hot, right? The database now takes those memory location and space them into something called the shared buffers, right? It's the database's own cache where those pages will be lived, so that hopefully someone will want to query something that is in the same page. So I just pull to the shared memory. Effectively, the reason it's shared memory because the databases will spin up multiple processes, of course. Most databases deal with multi-processes, and these multi-processes, all of these executing multiple transactions, they need to see a unified view of all the pages, and this is where the shared buffers are located, right? So that's what we do. So when I do a select ID, right, 1, oh, that's page 0. Oh, well, We don't really know it's page 0. We just scan. We read page 0. Now look, let's read row by one. Is the ID 1? Is the ID 1? Is the ID 1? Until we find it. If we didn't find it, we read the next page, page 1. And then if we didn't find it, we read the next page, page 2, and so on, right? Until we find that ID. And once we find it, we really have everything, because the page have all the columns in line. I'm gonna put an asterisk on that. So that's how things work. Now let's go to the reasons. Because now everything is there, why is select star slow? Right? Let's first go to the first reason. Kiss index only scans goodbye. First of all, you're right? If you're actually reading the heap, which is the table data, you're right. You have that select star, you can have everything. But here's what you miss on. Let's assume you have an index, like the student. Let's go back to the example of students, right? If I am a student and I have a table student, there's an ID field, there's a grade, there's a name, there's a bunch of other stuff, right? So now I have the student, there's an ID, there's a name, there's a grade, there's a bunch of other columns as well, right? So now assume I have a grade index. An index on the grades field, right? So if I do a query that says, okay, give me all the student IDs, I'm just interested in the IDs, that scored more than 90, right? A mark of 90 or higher. Well, if your grade index, and let's assume this is MySQL, right? Or SQL Server. And the reason I picked those two databases because they store secondary indexes a little bit different than Postgres, right? And we're going to come to the Postgres. It's very similar there here. So now, because I'm doing a grade is greater than 90, definitely I'm going to use the index that is there, right? So as I'm scanning the index, and again, scanning the index is going through the B trees, and the B trees have layers, and these layers store these keys, and the keys are stored in pages, and the pages are stored in disk. Very similar thing. It's just the data structure is different now, but the content is still pages. You're reading pages. Now, we have read this. We read through this beautiful index, and we found, as we're scanning, right, because the index is ordered, the grades, because we are having an index on the grade, it's ordered. So once I find the 90, I find 90 and 90 and 90 and another 90 and a 91 and 92. Everything is ordered. And because the value of the secondary index in the leaf page is the primary key, right? Again, this is, let's say, MySQL, right? Or Oracle if you have an indexed organized table, right? Then you technically have the ID, because they say the ID is the primary key, right? You have the ID right there in the leaf page, in the index. So you're done. Your work is done. Technically, your work is done. That's it. You found the grade. You have a grade, of course, is right there. And you have also the primary key, which is the ID, which is what you want. So it becomes what we call a covering index scan, or in Postgres speak, it's called index only scans, right? So you only really need to scan the index because you don't really need anything else. You just ask for the ID. But the moment you do select star, that optimization is just screwed. The database is, come on, you really had to ask for all the fields are. You really did have to do that. Damn it. Now it says, okay, you need the ID, but you also need the name, and you need the date of birth, and you need his documents and whatever, right? So now what the database needs to do is collect all these IDs, which are primary IDs, and now it has to turn around and do another lookup. It's called index seeks, right? on the primary key, hey, I found ID 7 scored more than 90, and 11, and 1007, and 10,008, and 20,007. They have to be random, right? Because you have no idea that the students who score more than 90 are actually in order, right? You'll be lucky, but it's never the case. This is called random reads. So random reads are the worst, right? When it's used to the database. Random everything is the worst when it comes to SSDs, reading from disk, reading of databases. You want to avoid those, but sometimes you can't, right? So now you have a collection of these puppies. You turn around and then do another scan or a seek on the primary index. So you say, okay, I want to find this student, this student. So you'll be scattershot all over the index, which will cause eventually many I/O to disk. Why? Because you just chose to do a star instead of asking for what you want. So really, really slow stuff. In Postgres, right? In Postgres, by default, when you just create an index on the grade, right? The Postgres always has to do that. Even if you ask for the ID, it has to go back to the table because Postgres secondary indexes, which is everything is secondary. There are no primary indexes in Postgres. The value is actually called the tuple ID, which is what we explained here, right? A tuple ID is literally a two pair, which is page index and the index of the tuple or the row in that page, right? That's what it is. So like this, in this particular case, page 0, 1 is the first row. 0.2, 0.2 is the second tuple, and so on, right? So that's what's happening. In Postgres stores these tuples, so it has to go back. But in Postgres, you also can have a covering indexes where you can create an index and you include columns from the heap, from the table in the index, right? Such that that index will have the ID or will have anything else you want. So you can get that beautiful index only scan. So if you have such index and your front end application, in this case is the backend server, right? That actually executes the query. In this case, it is a front end to the database, right? Will not utilize this beautiful index only scans. So that's the first case. Index only scans, you basically kiss them goodbye when you do select star, right? All right. You might say, okay, I don't care. The random reads affecting from this is really bad. Okay, let's talk about deserialization cost. Yeah. Correct. When you select star, the columns live in the page with the row. But getting them out and into the protocol that will be eventually delivered to the app will require something called deserialization, because these are just a bunch of bytes at this point. They are raw bytes in the page, because the page is just literally a memory. Once it's pulled into the memory, right, through, right, you malloc it effectively. It's just a bunch of bytes, right? So now you have to actually parse, right? So it's okay, there's this row, and this is the first column, this is the second column, this is the third column. And once you get the content of these columns, you actually have to coerce, you have to deserialize this from bytes down to the data type of whatever this thing is. If this is an integer, you cast it to an integer. If this is a long, you cast it to a long. If this is a double, you cast it to a double. If this is a custom data type, you cast it to this custom data type. If this is a string, you cast it to a string. That also has a cost. Not much, but it can add up if you have a lot of columns. So deserialization cost can really add up, because you don't really know how many fields that exist in advance, right? You soon select star, you have to do all of that stuff, right? And And that deserialization cost, again, we're talking about at the database level here, converting the page raw byte to data structure that then that data structure will be serialized, I suppose, down to the network eventually, right? But dealing with them into a number or a value, the conversion needs work, and it needs to be stored in its own form as a variable, as a data structure. So you're actually allocating more memory, if you think about it, just to store these things, right? Building those raw objects. All right. So that's the deserialization cost, right? Not much, but it can add up. Okay, not all columns are inline. First of all, what do you mean by inline when we say inline? Inline, when I say inline, I mean when I have a row store where the rows are literally one after the other. Row, all columns. First row, all columns. Second row, all columns. Third row, all columns. Just one after the other, right? The columns that are appearing inside the row are called inline, in the same page, right there. That's called inline columns, right? And you're going to see this word being used all the time, like inline functions, right? In compiler, like inlining sometimes gives performance things, right? But the problem here is, remember when we said pages are fixed size? I forgot to mention one thing, which is rows cannot really span multiple pages. If you have like a really big row with 20,000 columns, can't happen. But if you have that, then the row technically cannot fit it. You will have one page with a single row, and that row will not fit that page because it's so big, right? So you will have to spin up another page to complete that row. No. Database never allowed to do that, because the complexity to find the row becomes exponentially harder. So no databases, as far as I'm aware, allow rows to be spanned between multiple pages, just because of the complexity, if you think about it, right? So rows cannot span pages. Because of that, then Hussein, what do I do if I have one field of the string that has the entire work of Shakespeare in it? That's what databases do. Like, think about this, or blob, or lobs, right? Things that are actually binary, that are stored in as a column. JSONs are rarely stored in line, right? JSON documents, like in Postgres or other databases. You can't, because they can't fit a page. So what happens is, those are assigned a pointer. And when I say pointer, don't think of a C#. Don't think of a C pointer here. And it's a unique identifier that points back to that blob, right? So what happens is a marker is created, and that thing is placed on an external table, right? And MySQL has it. Postgres has it. It's called Toast. Right? They have to have it. There's no way out. You have to have some external place to store your stuff, right? They cannot fit into the page, right? And as a result, if you think about it, this actually what limits the number of columns. Why don't databases allow unlimited number of columns? Because of this reason, right? Because at the end of the day, you can have a non-variable static type integer, like the integer is not variable, right? It's a fixed size. It's either 4 bytes or 8, right? 64 or 32, right? If you have that, then how many actually, you cannot really put that outside. Doesn't make sense, right? As an integer, right? So what happens is you are limited by whatever the number of columns based on certain calculation. You can do the math as well, right? So what databases do is they take that long string, that long document, that long blob, that long JSON, put it in another table, put an ID to it, and that ID is instead stored in very tiny, like 1 or 2 bytes, or even less, inline. So that column only have the pointer, that identifier of the external storage. It's never stored in line, right? And again, it depends on the size of the thing, right? Sometimes if you have like 128 character, Postgres will say, okay, I'll put it in line. Right? There is a threshold to decide that. But mostly large stuff are stored outside, and guess what? They're often compressed. So there is a cost. If you actually say, give me that JSON, give me that document, give me that string, you're asking the database, yeah, you say, Hussein, it's already in line. No, I got this, but I have to now do another query to another table called the toast table in Postgres, the oversized something text or something. I forgot what it stands for. Okay? And that is an additional I/O, because that page where that toast exists might not be in the shared buffers. And as a result, you just caused another I/O. Look at the work you're doing. Look at the pain you're causing. You're causing pain. An I/O goes to the disk, and the disk suffers every time you hit it with an I/O. Right? Next time you do a select star, think about the suffering you're causing to all these equipments. Okay? I tried to say this with a straight face, but I couldn't. Okay, so especially that, because these sort of things are compressed, right? And you can disable compression if you want, but that will just bloat your storage. If you don't care about storage, sure. But then, not only you're pulling it from an I/O external, now there is CPU involved. Now you're making the CPU work for you, right? You're uncompressing stuff, because uncompressing has to be done in memory, right? Now it's just like, let me uncompress. Huffman encoding, whatever, right? gzip. All this stuff is happening now. Geometry stuff. You deal with geometry. I do with geometry all day. That's basically my 9 to 5. Right? Geometry stuff. GIS. Right? So yeah, this is really expensive, right? So doing select star, now you're silently, and the sad part is, if you ask the database to do all of this stuff, to pull all these blobs, to pull all these strings, and you just, in the client, you just say, I really just needed the ID. Well, I don't really need the rest of this stuff, right? It's like asking someone to bring you all this stuff, right? And bring you a dish of food or something, but you only take one thing. You say, I don't want that anymore. How rude. How rude, really. Okay, not all columns are in line, so be careful. Be very careful. Network cost. When was the last time you're back and running the same time, the same place as the database? Never. You never put the database in the same place as the backend, right? They never run on the same processes in the same host, right? Sure, they can run on the same physical host on a separate containers, right? But I don't know why would you do that, but you might have virtualization set up. But still, you have to separate them. There's networking involved, right? And of course, you need to keep them as close as possible so the latency is low, right? You don't want to put one in US West and the second one is, the database is US East, and the backend application in US West, and you expect queries to be fast. No, you have to put them in the same network zone, hopefully, right? And if you can't, then create replicas and have the replicas close by, right? I think I created one video at some point. I think it was clever, right? Keep your database close and keep your servers close and your database closer. I think that was clever, right? Clever way of saying it. Did I just call myself clever? As kids these days would call me cringe. So, right, network cost. So now that we talked about, okay, you selected all the fields, you took the hit, you avoided the beautiful index-only scan, you took the hit of database data structure deserialization from the page down to that thingy, right? And then you took what would you say? What else? Yes, you told me to get all these text fields and blob fields and JSON fields. So I had to go to a toast table, an external table, decompress them, and also put them in a data structure. So the double trouble. And then now I'm ready to send it back across the network. Now, each database has its own networking protocol, right? It could be, most use like binary specific representation. I didn't see really a unified, and this is something I talk about sometimes in my channel, where there is no unified database protocol. Doesn't exist. Every database just does its own thing. Right? Unlike the web, we have HTTP, right? It's a unified web protocol. Anything web, you go HTTP, right? And it's like the use cases went beyond web, right? It's everywhere, right? It's like this is the de facto standard. Some people brought HTTP down to the database. I don't know how well that performs, to be honest. But every database does its own thing. Like a SQL Server has its own, Postgres has its own, Redis has its own. Like everybody database is like, I want to build my own. And then now you have to serialize that data structure you have down, serialize it down to bytes, down to this protocol language that you have, right? So the serialization aspect to that protocol, application level protocol, right? Your application, that the database protocol application in this case, right? Whatever that structure is, right? And then that goes into the transport protocol, which we don't have anything else, TCP/IP. That's all what we have, right? So it goes down to IP packets, and then segments, sorry, and then IP packets, and those IP packets are shipped, right? So now, if you're sending really large columns, the response from that protocol, the database response, the database SQL result will be so large such that the network transmission, you will feel it, especially if you have like larger latency, you will feel it, because now I need to write, and the maximum I can write at a time is the MTU, which is the maximum transmission unit, defined by the IP layer 3, and that's basically is defined based on path discovery MTU, right? The protocol that discovers what is the weakest link in this network that I'm transferring, and says, okay, what is the minimum I can send, or maximum in this case? I can send 1500 is the default in the internet. You can send lower. There are some routers like support like 500, like very old routers, but 1500 is the standard. There are routers with jumbo frames that suppose like 9000 and stuff like that, and they're even large, but that's the kind of standard. So you can only send 15 bytes at a time in the IP, and it's even lower at the TCP segment layer, right? I know I'm going into very details, but this is the point. All my videos, I always go into details, right? I don't make like 1 minute videos and done with it. I like to explore these things because I am passionate about this stuff. So I apologize if you don't like this content, but I really do like to go into these details and kind of brush everything, like understand everything, remove the black boxes. Yeah? So now, if you have a lot of data, even if you do compress it, which is an additional CPU database overhead, then you still have to transmit it. And the conjunction algorithm protocols and slow start will allow you to send multiple of these 1500 or 1460 segments without waiting for an acknowledgement, right? And initially, you're going to send 10 segments at a time. Like Google increased the initial window size for the conjunction window to 10, I suppose, because like there is no point. The internet is really fast these days. So let me send 10 at a time. So 10 times 15, that's like what? That's 15K. So that's 15K, right? So you can send 15K at a time if you want, right? At a start, right? And then but not all network supports that, right? So it always starts slow and then it increases slowly, right? Incrementally increases. So now as you go through this, you're sending that, but eventually the client have to start acknowledging this. It has to process this, and the client only acknowledged something that actually was able to receive, right? So if there is a data loss, guess what? The client didn't receive it. The server timeout will hit, and then will retransmit it. So all of this, you'll feel it. The more network you have, latency, the more you will gonna feel it. Yeah? That's why it's like I always feel like applications, if you want to really test applications, like when it comes to performance, like just put the database and the backend in a very really far apart. Right? I know it's a bad idea, right, to do that in production, but it will force you to optimize, because you're gonna send as small as possible and you're gonna receive as small as possible data. You're gonna say, okay, why am I sending this much? Let me send less. Right? So it's like putting yourself in slow mode such that you feel the pain, right? Of these kind of things, right? So returning all columns require deserialization, right? Of these large columns, such as strings, blob, the client will never use. That's the sad part. All of this, you're incurring all the high cost of transmission for nothing at all. And then we finally talk about the client deserialization, where now that the client received all these raw TCP segments from the NEC actually transferred it to the OS through DMA, and then that becomes just raw bytes, and the OS now just say, okay, what's for this listener? Where is this going? This is IP, this destination. All right, it is this socket. So it will start transmitting your data to the client app, which is the basically, if you have Node.js, that's the Node.js app, and specifically the library that you use for the database client, right? So if it's a Postgres client, that will be that library will be called, and you're at the mercy of how this library is authored. How is it parsing the protocol? How is it understanding this stuff? That's why lazy parsing is also a thing in the client side, where let's actually wait for the client to consume some of this stuff, such that you can avoid the head of client deserialization and client building all these objects. Fetch has the same thing, by the way, right? The Fetch API. Fetch API, when you call it, it will give you the headers only. It will give you the response, but it will give you just the byte, the raw body, right? You cannot actually do anything with the body until you call body.json function. So go ahead and actually take the head to actually deserialize it. And the reason Fetch does it this way is because you might only need the headers for some reason, or you might only need the response code, right? The status code or content length. So this is the way such that the client will consume what it needs, and when it actually needs the content, the body, it will do JSON or .text to actually move it from binary down to the deserialization, down to the data structure. In this case, it's JSON, because compared to JSON is expensive, right? Now, I'm assuming it's the response is JSON in this case, right? And so the deserialization is costly. So if you can do it lazily, that's even better. But how about that? If you can avoid sending data that you never use, that's even better for the backend, isn't it? Right? So yeah, guys, that's all what I have for you today, right? So we talked about why select star is really slow, really slow. I might have missed the reason or not. Let me know in those comments down below. Hope you enjoyed this video. I'm gonna see you on the next one. You guys stay awesome. Goodbye.